the Kalman filter. Now, I am not going to be able to do justice to the Kalman filter as it needs. There's classes that are taught, whole semester of class taught with the Kalman filter. I think Professor Mehta in ME, he teaches a class on Kalman filtering, and it's everywhere. That's the thing. So if you get into adaptive control at all, sometimes it depends. ECE 517, which I don't know what's cross-listed in ME. That's either, it depends on the professor. They can teach you nonlinear control in that class, or they can teach you adaptive control. And these Kalman filter equations are big, and then they're all through adaptive control. I'm sure in many, many different places. So there's a lot more background here for the Kalman filter. What this lecture that I'm going to give here these next 2 days, I take this, I don't take full credit for this. I had a grad student help me with these lectures a number of years ago. And also I got a lot of these ideas on how to talk about Kalman filtering the first time from Professor Tim Brettel. And he's an aerospace professor, if you don't know him. He's teaching that quad rotor class, AE 483 right now. I wish that class is just, I would love to say go take that class, because there is some neat things they learn in that class, AE 483, but it's a required course for aero, and so there's no room for anybody else in that. There's 120, 130 people in that class each semester, or each fall semester. Anyway, but the neat thing, and what I'm kind of excited about, you're going to see today where I'm talking about these, what are called the covariance and the trust that you have in your model, trust you have in your sensors. They did a neat lab with those little crazy fly quad rotors this semester, and they actually, you're going to see, I'm going to put up here like what's the variance of how much this trust and the variance in the measurement that you've gotten and all that. They did some neat little experiments where they launched the quad rotor, moved to along in a square, and as they were doing that, they were kind of seeing how well the quad rotor tracked that, and they found the variance, and so what the neat thing about the Kalman filter is you don't need to actually find the exact variance trust, but it's more important if you find the trust of something related to something else. So it doesn't have to be the actual, variance of the sensor reading, but if you can do that, that's a neat way to do it. So I've not actually done his lab. I'm excited to do that probably won't get till the summer, but to see how you can actually measure some of these parameters and stuff like that. What I've always done with the Kalman filter is I kind of guess at it and find a relative range, and you'll see what I mean by that. And then it still works, which kind of a beauty of the Kalman filter. But anyway, so again, not going to do justice in these 2 lectures, but let's see what we can do, get you understanding it maybe a little bit more, and then definitely if you're interested in this, you should take another class in the Kalman filter. So anyway, okay. Well, I like to, and if you haven't had observers in a long time, this may not be the greatest place to start, but maybe you've had a class. If you've been in ECE 515, for example, this would be very well known to you. The other class would be SE 424. We get into this a little bit. ECE 486 gets into this a little bit, and my SE 420 class that I teach with Dusan Stepanovic get into this also. But the idea here is that we have this hat state right here, right? This is, and you're familiar, maybe more familiar if in other classes, familiar with the state space model of x dot equals ax plus bu, and then y equals cx, plus du. And in most systems, d is 0. So, but anyway, you should be familiar somewhat with this state space model. And the idea is here, right? You got to pick your states, whatever they are. You know, maybe x1 is some theta, and that's what we use right with the what am I trying to say? With the Segbot, right? x2 is equal to theta dot, the tilt rate. x3 was equal to our velocity, right? Whether it's psi dot or whatever we called it. I think it was psi up there, wasn't it? I got them mixed up. I'll just get rid of that and say wheel speed. How about that? But, so those are different states, and then given those states, you can form this state space model. Okay? Well, maybe we know the model and all this, and then when you discretize this, the discretization, a lot of textbooks then changes from xk plus 1. So what do we predict our state's going to be a step ahead in time? 4 milliseconds later, 5 milliseconds, whatever our sample rate is. Some textbooks change that a to f, and that's what I have in my notes. fxk plus, what is it, g? I got it right here. Where did it go? I'll go back to it, Dan. Is it g? Yeah, g, and then, yeah, okay. Well, there we go. Plus g times u. And this is a discrete version of it. So where we worry about the poles being on the left half plane in a continuous model, the discretized system is, again, in the z domain, and stability is if you're inside the unit circle, and the z domains, j omega, or well, it's plane or whatever, the z plane. Okay, but anyway, what is this? So let's say we know this model, right? What that's saying now is, can we estimate these states in our DSP, in our computer? Okay, and so the observer, right, is this right here, where it says, okay, I'm going to estimate, assuming my model is correct, right? That's what it's making, a big assumption there. I'm going to say, okay, I know this f, so I'm going to, inside the computer, calculate what I think the next state, the states are going to move to in 4 milliseconds. And we're going to multiply, because f we can identify, we hope, right? Depends on the system, but let's say we can identify it. It's not going to be perfect, but it's going to be close, hopefully. So, and then we multiply these constants of f. A lot of times, a linear system, f is just a bunch of constants, plus gu. But then to get it to converge quicker, we will have, and I always get the minuses mixed up. Let's make sure. Yeah, plus L, there we go. So then plus this L matrix. This is something you have to design. This L times what? Well, it's our measurements, our estimations minus our measurements. Is that true? I always get, again, I want to get the minus signs correct. I should have this both up. Y, yeah, our measurement minus our estimate. Okay. So yk, remember here this cx, or this would be the same thing. Yk equals, a lot of times they change that to h xk. So our measurements, the states that we can measure are our yk, and then subtract that from our estimates, our estimated, which is really simple. That's just simply y hat k is equal to h times x hat k. Anyway, okay. So the idea is, can we come up with this L to make the estimate converge to the real states? That's the whole point of an observer, or sometimes it's called an estimator, and all that. Well, this L in this for the observer, this L is found offline. You kind of say, well, okay, if this is my F, this is my G, and more importantly, if this is my F and my H, can I come up with the L that tells the estimated states to converge very quickly to the real states? The thing, now it's not exactly this equation, but the Kalman filter, what is it does is it replaces this L somewhat with a game they call K. Okay, so there's another K gain. It's different than our K gain for balancing the Segbot, right, and all that. So they call this Kalman gain K. And can you come up with this K if instead of, well, you need to know your system, but also by knowing how much you trust your system and how much you trust your sensor data and all that kind of stuff. And so it's different than this design of the L matrix in the observer, but looks a lot similar, okay? And so that's why I start with that first. Now, we've been doing this. What did we do with our, when we were trying to find the XY position and the bearing of the robot car as it was running around? We found that that wasn't super accurate, was it? But what do you think? If the robot was here and it goes forward for, you know, 5 samples, what, that's 20 milliseconds. Do you think the robot knows where it is pretty good? I'd hope so, right? I would hope at least there's no slippage right there. Again, always assuming no slippage and all this. But for a few samples, the robot knows where it is pretty good, right? It's not off by as much. Now, if we go around for, 2 minutes, we don't know where we're at all, do we? Okay, probably. But initially, we trust that each sample, actually probably pretty good. And what do we do there? So let's, in that case, let's for now just make ourselves a little bit simpler. Let's forget about bearing. Well, I don't know if we can forget about bearing, but anyway, so we would say that, now, yeah, that gets it confusing here. Let's do this. Let's say, I'm going to say X pose, our position, K. What we did this too, X pose K. Well, what did we do in our code? We said that that's equal to, we integrated, didn't we, velocity. So X pose K is equal to X pose K minus 1. Remember we did this? Plus what? We took our average wheel velocity, so whatever that was, theta dot left plus theta dot right divided by 2. We multiplied that by delta t, right, to give our little step in velocity, and then we multiplied that by sine of the bearing. Psi, what, I don't remember what we called the bearing, but whatever, bearing. Agree with that? That was something we did. And then, of course, we said y pose K equals y pose K minus 1 plus the same thing, but cosine, remember? Delta t cosine the bearing, okay? And then, yeah, we could do the we could do the wheel difference to get our psi and everything too, whatever. Psi k equals, and we could find that out too. But let's just focus on these. So the idea is here we've got this giving us where we are x, y in the course. Maybe we have something else telling us where we're at x, y in the course. There's a group that's going to be, I think Philip and Chris, right? They're going to be looking down. They're getting a camera, and they're going to put some locator tags on the robot. Okay, and they got this camera that's going to be looking down and finding where those are. The robots are, or robots. I don't remember what they're doing. Where those are located relative to the camera. Okay, and so they're going to have somewhat of another estimate x, y of where the robot is. Okay, we could do that outside with the GPS, couldn't we? We could do it in my lab. It's very much cheating. That's why I'm not letting you do it for this one. But we could do it with the motion capture system, those 24 cameras that are in the lab also. Okay, then you need the little gray balls and all this kind of stuff. Well, the idea is, how do we, given that we know where we're at, x, y, with this prediction, okay, and now this new data that tells us, hey, I think we're at this xy position, right? How do we fuse that data together? That is this idea, one of the uses of the Kalman filter, this sensor fusion. Okay? Well, the idea is we're going to call this the prediction step. Okay? So this is what we're going to call our model. This got me at first when I started playing with the Kalman filter. You know, I always think of the model of the system, a dynamic model, because that's what I always use in control systems to decide what my PID gains need to be if I'm doing it in simulation, or what it needs to be stabilizing. But a lot of times, now, some people get even more deep into the equations, but really, for a robot, we need to know where its XY position is, so its kinematic model, not its dynamic model, right? Now, it'd be nice if there's a way to take advantage of the dynamics also, but again, since you know, sometimes the data, like for example, the GPS, you get GPS data like every second, right? It's not super, maybe you can get some faster possibly, but the cheap GPSs out there, and I would guess even the GPS in your car, they're not getting data every millisecond, for example, all right? And so some of the dynamics aren't as important when you're getting stuff that slow, all right? Anyway, that could be the same case for like a camera looking down on our system. But anyway, so the model now is the kinematic model, and then you can play with it. You'll see papers where they pick out different types of, you know, different models that they want to use in the Kalman filter. So that can be a confusing part. But anyway, what we could do with the robot, now of course what we're getting to, I got to get to by the end of Wednesday's lecture, is the Kalman filter for the Segbot, right? Which is a little different here, but I'm trying to kind of explain what's going on with the Kalman filter. So we've got this prediction step, okay, and then we need a correction step. Okay, and here what we're mainly doing is we are saying, okay, this, I have my states. Let's go back to just still, I'm going to just do X pause again. So X pause K, yes. What we have, right, is our X pose K given, let me think. Okay, what this is saying, well, how am I going to write this? Let me think. So let me not worry about it. So we're going to say, all right, what, my corrected state, X pose corrected, let's call it that. Just to not worry about what the exponent, the sub x, k plus 1s and k's and all that gets a little confusing. But my X pose corrected, what? It's equal to what my prediction is, X pose prediction, plus what? Well, here comes that K, plus our Kalman gain, could be a you know, multiple, it could be a matrix, right, and all this. We're going to find with the Segbot, it's just a single constant, but, well, a varying constant, but with a multi-state system, it can be multi-columns and rows, okay? So we have to figure out that with the model. And it's multiplied by a measurement, and in the Kalman world, we call that Z. So this would be a different measurement. So a different measurement go up, come on, there we go. Different measurement of X pose and Y pose. So Z would be a vector, right, of two things. Again, I'm ignoring bearing right now just to make this a little bit less things to write down. And so it's K times, let's erase this, Z minus our X pose prediction. Yes, right? Yeah. Yes. Minus this same thing, X pose prediction. So what do we have here? So we are saying, hey, this is what I think I'm at. Now this measurement, this other measurement, the camera, the GPS, or whatever, says, no, I think you're here. Okay? So we find the error between what the measurement gives us and where we think we are with our prediction model. And we multiply this by this magic gain K, and we have an improved or corrected X pose. Okay? And even if the measurement, it's interesting, I don't know if I'll get into this as we go through, but if you think about these variances and probabilities, even if this measurement isn't super great, all right, we don't trust it a lot, but as long as we trust it somewhat, this corrected X pose is actually has more trust than the previous prediction. Okay, so which is kind of cool. The other neat thing about this, and we're going to get into more of an example. The other neat thing about this is you do usually your prediction step, you do at a certain sample period. Okay, every 4 milliseconds, every 1 millisecond, whatever we're working there. With the Segbot balancing, we're doing the Kalman filter every 1 millisecond. But this correction step doesn't have to happen at the same rate as your prediction step. It's whenever you get new information. That's very nice for you guys using the camera, because the camera looking down is not going to be able to get an image every 1 millisecond. Okay? It gets an image every 30 milliseconds. And the beauty of the Kalman filter is you can do this correction step whenever you get a new measurement. Now, of course, if it's every 20 seconds, it may not help us too much. Right? So it depends, or whatever, But if it's at a good rate, it's probably going to correct and keep us on track. The biggest thing, right, with these equations up here was that if the wheels slip or the radius of the wheel is a little off in our model or whatever, our prediction is drifting, isn't it? Okay? This correction pulls that back in and keeps us on track, right? Because hopefully this other measurement doesn't drift in that sense. It's more as like a camera sitting there. It's at least fixed in space. So hopefully that doesn't drift as much compared to our dead, what we call, this step up here would be called dead reckoning, right, in a robot. Okay. All right, so that's kind of a big overview. Let's think of a one-dimensional case, okay? And and see if this helps talk about the Kalman filter for you. And again, I got this idea from Tim Brettel, so just a neat idea here, just to think about it in terms of a one-dimensional system. So and I'm going to put this PowerPoint that I've been showing up at the box folder, so take a look at this more, and I got a little more description. But let's say, in this example, we have a ultrasonic sensor and a LiDAR sensor, okay? And we have encoders on our wheels, and we can predict where we're at going forward. Let's also imagine we can't turn, right? There's no turn command on this robot, so all we know is our X distance to the wall, okay? And what you did is you did a bunch of experiments. Maybe you started right here, 5 feet from the wall, you moved, and when you got 2 feet from the wall, you stopped. Or something, where you think 2 feet from the wall is with your prediction. And then you actually measure that with a ruler and all this kind of stuff, and you find the statistics of how close you are to 2 feet away from the wall when you stop. And you repeat that experiment, I guess, right, over and over, and you get some probability. At the same time, as you're going forward at that 2 feet, you take your ultrasonic measurement. And that gives you a certain distance from the wall. You measure it, measure the distance, and you get some statistics of how much the variance is for the ultrasonic sensor. And then you do the exact same thing for the LiDAR sensor. All right, is that kind of making sense? Now, so let's think about that. So let's say with the statistics here, what if we, let's get the numbers out here. So when we do that, the model, so we'll say our model at that X model is saying that we're at 2 feet or whatever, what did I say, 2 feet away from the wall. And that has the variance of equal to 0.5, the bell curve, right? So Gaussian noise or whatever, Gaussian distribution. Also, now this is a little weird. I pulled these numbers so they're kind of far from each other in my plot when I show it here. Don't go by, these numbers. But the X from the ultrasonic sensor says that it's at 4 feet. That's a big difference, right? But anyway, 4 feet away from the wall, and it's got a variance of 1. Okay? And finally, we have an X from the LiDAR. Is it the LiDAR? I think it is. LiDAR, or whatever other sensor I say. And it's saying really crazy, it's at 5, but it's got a variance of, what is it, 1/10? I think so. Variance of 0.1. Okay? Yes, 0.1. So, without thinking about all this Kalman filter stuff, you could kind of come up with a way to fuse all this data. And let's think of a way to do that. Okay? So, what I'm going to be talking about, variance, and then trust is the inverse of variance. So we trust this model with a factor of 2. Okay? We trust the ultrasonic sensor with a factor of 1. And then we trust the LiDAR sensor with a weight or factor of 10. Okay? So first, do you guys have any idea what you could do to fuse X model and X ultrasonic sensor first? Given that we would weight or trust or weight the X model twice and weight the ultrasonic sensor only once. What would you intuitively do? What do you think? Yeah. Sure. So what would we do? We would say that now our new X best, our best guess, or whatever you want to call it, of X is equal to what? You say a weighted average. So we take the model 2, what would we multiply it by? The trust, because we weight it twice. Does that make sense? Good. So we weight that twice, and we add to that 4. What would we multiply 4 by? The trust again, right? 1. And then what would we divide that guy by? That summation. So a weighted average, right? You would take the sum of the trusts, right? So 2 plus 1. Does that make some sense a little bit? Okay. So if we do that, we get our X best equal to 8/3. Okay? And how much do we trust that now? Because that's the other thing. Once we do this, correction step, we also have to correct our trust in that X best, or whatever you want to call it. So that variance. Well, we would trust that the same, the sum right here. This would be our new trust. So we trust that with a factor, a weight of 3 now. Okay? Yeah, a little, not maybe quite intuitive, but that would be a way to fuse those two sensors, right? And then we do the same for adding on do one sensor at a time. Now we've got this new X-best, but now given the LiDAR, okay, we now have some more to do, in other words. And what do we do now? We fuse this guy with the LiDAR. And so what do we say? We say, when we're summing these again, we take our trusted, 8/3 times the trust 3, weight that one with a factor of 3, and then we take our 5 measurement from the LiDAR, we multiply that by a factor of 10, okay, and then divide by the total trust, 13. That gets becoming a little ugly number, but it's what, 58/13 or something like that, right? How much do we trust that? So our final one, 58/13, and we trust that, come on, erase. We trust that with a factor of 13, don't we? So that by the end of that, with our two measurements, we're saying that we would say the X coordinate should be this guy with a level of trust right now of 13. And then we would go back to just doing our prediction with this starting out our prediction and continue to predict from this new X best every millisecond or whatever. And then when we get our new sensors, we do our correction. So let's just look at that a little bit in MATLAB. So that same analysis, if I run this, so the idea is, again, assuming Gaussian distribution, right? We have our prediction that we have a value we think is at round 2 with a variance of 0.5. So the inverse of that is our 2 trust. And we're going to fuse that with the value that only has a trust of 1 from the ultrasonic sensor. Okay? And then as we see, the trust always increases. So in other words, the variance gets narrower, isn't it? And so when we add those two together, or combine those two, now we've got our new best guess, or our new best, at where we think we are X away from the wall. And then we get this next sensor reading, or we got them both at the same time, so and we just fuse the next one. And again, I'm saying this is crazy, but just kind of spread it out for this chart here, for this plot. Now we say, nope, I think the LiDAR thinks we're at 5 feet away with a trust of 10. So that's going to bring us pretty close to that one. But again, a little bit narrower trust, or narrower variance, which a larger trust, giving us this, no, I think we're at 4. Okay? What do you think about that? So, this being a way to fuse the data, can we make this look like the Kalman equations? Okay. So, this is where it gets a little messy, and we'll talk about this next lecture also. But what do we have? We can write this all out. We can say now, what is our equation? Well, we've got that, and I just got it in front of me here so I don't make a mistake, hopefully. We have this thing we're calling X best, right, is equal to what? This is the correction step. I guess we should first look at the first order, or the single degree of freedom equations. First, the model and the prediction step. We just say that X, oh my, what did I just do? Back to here. X best is equal to X best. Sorry. Let's take that back. Let's do this better. X prediction equals our old X prediction plus delta t times our velocity, and actually minus. So in other words, we're getting closer and closer to the wall for this little model. Remember, the robot can only move forward, and it's getting closer and closer to the wall. So that's our prediction step. Okay, we got to talk about what the variance of the prediction is, and we'll talk about that next time. But we do have to keep on updating the variance, how much we trust every time we do our prediction. So we're going to find that this k plus 1 or whatever, that's equal to just some q constant of how much we trust the variance of how much we trust our model. And we'll come back to that q next time. But anyway, now, since that's our prediction, now what is our correction? We just did that correction. And so then we have our x best, our new corrected value, is equal to what? Well, we said we take where the x best is, okay, sorry, x prediction is, I'll get this straight, x prediction at certain time, times how much we trust that, which is this 1 over this variance of the prediction. Agree with that? That was our what we were doing right here. We were taking our where we think we are prediction, and then we're multiplying that by the trust, right? So we have that this is our trust, 1 over the variance, plus our x sensor or ultrasonic or whatever, x sensor times its trust, variance of the sensor. Okay, and that whole thing divided by the variance of the prediction, 1 over the variance of the prediction, the trust, in other words. Remember, we summed up the trust, plus 1 over the variance of the sensor. Okay, so we've got that equation. And then, of course, we got to be keeping track of the variance. So, let me think. Right. So, our variance best, or 1 over our trust, variance best 1 over is equal to 1 over the variance of the prediction plus 1 over the variance of the sensor, right? So in other words, the sum of the trust right here. Sorry, so these are two equations. Gets a little confusing there. But these are the two things we have to solve for each correction step, don't we? We want to know what our new best prediction is, given that new measurement. Well, okay, and I'll go into this a little bit more next time, but if we say that k, and I'll go through the math a little bit just so it's not magic to us. If we say that k is equal to the variance of the model or prediction divided by the variance of the prediction plus the variance of the sensor, we'll find that this falls in line. When we choose like this, this makes the 1D case that we can kind of comprehend with our minds, because when you start going to matrices, it's hard to understand. But when we do that, we end up with the following form of the equations. And I'll just go back to the PowerPoint for now. And again, we'll talk about this a little bit on Wednesday. And this describes this example right here, these pages. But what we're going to do is we're going to rewrite these equations really quick. But here's what I just wrote down. But then choosing that k as I did, where k is this, we can put this in this form. So this is the correction step. We say that our new best guess is equal to what our model's been saying plus k times our measurement minus our best, our estimate, right? So this is that error I was talking about, and K times this gives us our next prediction, plus right here, 1 minus K times the variance of the model gives us a new variance, how much we trust this new corrected state, right? That will then just assume we're at. That's where we'll assume we're at and continue on from there, given this K right here. And then what we'll talk about next time is this looks a lot like the matrix set of equations, where we can go and create the prediction step. We got to talk about that. We can create this term called S. What is our K? And then what is our correction step? The reason we need to pull out this S term is because when it turns into a matrix form of equations, we can't just divide by S, we've got to take the inverse of S, don't we, if S is a matrix. And that's computationally expensive, isn't it, to take especially if you start getting larger and larger S matrices. And then again, I just like showing this 1D case, and then maybe it's a little bit more easy to swallow these matrix set of equations that form the actual Kalman filter. Okay? And so that's what I'll finish off with on Wednesday. This is a real quick introduction to this. You know, we spend whole semesters talking about this in other classes. And again, you know, proving why this works. I'm not going into that at all. I mean, I would have to take that class to prove to you why it works, okay? I got, you know, my background with control and the observer estimator design. I'm sure it has some very similar, very similar methods to prove that this causes the error term to converge to zero. That's the whole point, right? That's the point with a PID controller. That's the point with control. You know, you think about control of a system, you always think in your mind, what is my error terms? What am I trying to drive to zero when you formulate your problem? Okay, what am I controlling? Well, where is the error in that term? You know, so, and it doesn't always have to be error in position or error. You know, we do some controllers, error in energy. We want the energy of the system to converge to a certain energy, and things like that. So, well, there's all sorts, heat, temperature, right? There's all sorts of feedback that you can institute into or put into a control system, use to control something. So anyway, yeah. Now, so where did we leave off last time? We kind of had this little example where we were just had the robot moving straight, couldn't even turn, and it was just moving to the front wall. And we were predicting where the robot was. We had two sensors that told us an additional information of where we were to the front wall, right? And last time we kind of went with all this variance, this Gaussian noise distribution of these statistics we're taking with the sensors, with the model of our system, and we remember that our model was simply what? We just saying that, where did it go, right? Write down the right thing here. Right here. So just that our position, X, and we're going to call this X prediction, okay? X prediction equals our X prediction previous, like a K minus 1, this is a K, right? Minus time times velocity. So we're doing a very simple integration there. So that's like the backwards rule or forward rule, I don't know. We're not doing the Tuscan rule here. We're just taking one velocity, we're hitting it by time, and subtracting it from prediction because we're always getting closer and closer to the wall, right? So that's what we're saying our prediction step is in this little example, okay? All right. And of course, what we did with the robot car is we did XY as we were moving around. So we'd have two states, but we're trying to do a simple 1D case to kind of show these equations. Okay, and so what we kind of talked about last time is then, okay, great, we've got this prediction step. Now we've got some new information. We've got this sensor reading from ultrasonic. We have this sensor reading from a LiDAR. How do we fuse those together? Okay, and what we talked about is we do this with like a trust factor. Okay, and so we have this X corrected, we'll just call it X correct, is equal to what? What did we say? We'd say it's the X prediction times what we trust it to be right now. Trust of predict. This is going to get ugly with, but so, right, we weighted this. We weighted that prediction with the trust that we have, a weighted average. And then we said, okay, but we got this sensor reading that's telling us another distance we are away from the wall, right? And we multiply that by our trust in the sensor. Again, I've never taken a system and gone and figured out directly what this trust is by gathering a bunch of data and all that kind of stuff. What I've been able to do in the few Kalman filters I've implemented, I've done it on 3 systems in my history, how many systems I've done Kalman filtering on. I've been able to just guess at what these are and play with it until the system converges nicely to the corrected state. Okay. The neat thing about Kalman filter is one thing you can do is you can collect data as the system runs around the floor or whatever, and offline you can run through and play around with these trust factors. You don't have to do it just as it's running around on the floor. The other thing that helped me with the Kalman filter that I'm going to talk about on the Segbot is there's another type of filter for fusing the data that's out there that maybe you've heard. And if you're interested in a paper on this, I know of a really good paper on what's called the complementary filter. That's another way where you can take one measurement and hit it through a filter, and then another measurement and hit it with another filter and fuse those two together. So I had the advantage with the Segbot, at least, that I already knew how to stabilize it with the complementary filter. Then I was able to go through and form a Kalman filter that did the same thing. Okay, so I kind of cheated there a little bit, because with the Segbot, to try to tune it without having something that stabilizes it is pretty difficult because it's an unstable system. So luckily there, I had something that already could stabilize it and then collect the data that I could take offline and play around with these trust factors. So, it's a little bit, so as I said, and maybe talk to me in a year or after the summer, I'm really interested, as I said, Professor Tim Brettel, for his quadrotor class this semester, actually went through and measured all these statistics with a little quadrotor, and maybe I'll be a little bit more educated on how to do that with, say, the Segbot or something like that. But anyway, what's neat about the Kalman filter is it's really just the relation, the relation between these two, more than it being the exact trust we have, statistical trust in this sensor data. Now, anyway, so we have that, and then of course it's a weighted average, so it's divided by the total new trust which we have, which is trust prediction plus trust sensor. Okay, all right, and great. Now, what we're going to end up doing, the Kalman filter is more into what the covariance matrix and all this kind of stuff. So it's more interested in the variance of these sensors, which is 1 over the trust is what we're going at. And so we want to put the equations in terms of variance instead of trust. And then, of course, we have to always keep up track of our trust or our variance, 1 over that, trust corrected is equal to just the sum of the trust right here. Trust predict plus trust censor. Okay. So now, I don't want to do all the math here, but let's take it through a few of the steps here. So now what we have, if we take these two equations and now put it in terms of the variance of these different ones, it gets a little uglier, all right? Because we have to have 1 over all these. So x corrected, what are you doing? Okay, fine. X correct, I can go here, draw, no? Why does it do that sometimes? Of course, when I don't want to, forget it. You got a little jagged edge there, fine. X correct is equal to, now, X predict times 1 over variance predict, right? All this, I'm not going to write it all out because that'll just take too much time. And then, of course, X, what would this be? Censor times 1 over censor variance. And then this is 1 over variance predict, 1 over censor variance. So nice and ugly. What it ends up being is, dot, 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 dot. What it ends up looking like nicer is X correct is equal to X predict times the variance of the censor. Yeah, as we multiplied this all out, variance of the censor plus X censor reading times the variance of the prediction. Or at least this is one way to write it. You could write it other ways. Over variance of the censor plus variance of the prediction. What is going on? Come on, pen, be nice to me. It's not drawing. Okay. What can I do to get rid of this? Go back, maybe? Will it be out of it? There we go. Being flaky today. All right, X correct variance prediction. Okay, so that's just another way to write it. Now, in addition, we could put this, we could divide, right? We could have this term right here divided by this guy, and then the same thing here, right? We could divide this into 2 terms. And what are we looking for? We're looking for to write this equation in some kind of, in terms of an error, which is our censor reading minus our prediction. That's what our goal is. We need this error term. And that error term is something that we would like, in some ways, to drive to 0, okay? Depending on the trust between the different ones. So we're looking at this error, and this error is determining how we need to correct the states, right? Well, what ends up happening after you do a little math here, we're going to have the Kalman gain is equal to, and this is going to form look like the same equations when we get to the matrix equations for the Kalman filter. Variance of the prediction divided by variance of the censor. You're going to see in a little bit, we're going to call this R. Okay, the error, the 1 over how much we trust the censor reading. Okay, we'll call that R in our Kalman filter, plus the variance of our prediction. Okay, so that's our K gain. Okay, and what ends up happening, if we do a little, so for example, if you're interested in this and want to see how the math goes, see this right here, this variance of the censor divided by the variance of the censor plus the variance of prediction. That right there is equal to what? Let's see here. So where do I have that? Right here. So variance of the sensor over variance of the sensor plus the variance of the prediction step. That can also be written, make this 1 here, right? We can say variance of the sensor plus variance of the prediction over, just a little trick here, that's how they work these equations, variance of the sensor plus variance of the prediction. See what I'm doing? This is 1 right here, obviously, right? So I made this term 1. And if I subtract from that variance of the prediction over variance of the sensor plus variance of the prediction. So what I just did, I pulled out here, look at this. Here's our K, isn't it? Right here. So this little guy right here is also equal to 1 minus K, is what I'm trying to pull out there. So doing little tricks to make this look like, or put it in the same form, put it in the same form as the Kalman filter equations. Okay, and so in doing that, what do we have here? This right here, this term by itself, what I got circled, this is x predict times 1 minus k. See that? This right here is x predict times 1 minus k, and then x sensor is already in terms of k, so x sensor times k. Kind of see what I've done? So we have then that x correct is equal to, it's equal to 1 minus k times x predict plus k times x sensor. Okay, and then notice what we've got. We can merge these k terms, and now we have x correct is equal to x predict. So what we've been predicting, to that we correct it by the factor k times x sensor minus x predict. And we've got our nice error term right there. Okay? And so here we go. This guy is our error term. We multiply this k. And this k, depending on, the different data that's coming in, these trusts in the sensor could actually change as time goes on. I've never done a Kalman filter like that, but I'm sure that could happen. So this k is never staying, well, it can converge to a constant or a value, but it also can be changing depending on what's going on with the system. So that's the nice thing, where with an observer, that L matrix you design is always staying the same. Okay? That's the beauty of the Kalman filter. And again, that's where, the crazy math folks can prove this all to us, right? With this thing changing all the time, is it optimal? Is it doing what it's supposed to be doing and all that? That's all the math behind that people have to show. But anyway, that's what you get in a class that, you study this the whole semester. But, in our case, because we're trusting the sensors the same amount with the Segbot and all this kind of stuff, that K actually converges to a number. Okay? And it pretty much stays the same after about, I don't know how many samples of running the Kalman filter. Okay, but anyway, so now we've got this in this Kalman form. Okay? Good. And with the same kind of math, just kind of little tricks to run through with this K value, we also have that our variance corrected is equal to 1 minus K times the variance predict. Okay, the variance predicted. Okay, so this is our final form, these two equations of the correction step. All right, good. Anyway, I just think it's kind of nice to see that it falls, just doing this kind of, as we say, this like weighted average that's somewhat is kind of makes sense in our brain, right? If we can think in those terms, how that actually falls out nicely to be in the form of the Kalman filter. Now, I haven't shown you the form of the Kalman filter, have I yet? But let's do that. Okay. So let's finish it off. Let's go through the whole thing. So we have, and that's what the Kalman filter will do too. We have our prediction step. That is, and again, with our little example here, that is, and we're going to now go in the Kalman terms. So we're going to call this X. Yeah, let's go ahead and call it our estimate hat, or prediction. K plus 1 given K permit. These subscripts are a little confusing. But the way I read this is I say, this is giving me my next step prediction given previous information, right? That's what I'm saying there, giving one step back information. Okay, that is equal to what we predicted last time, last sample, and then again for our simple equation, minus t times vk. So this is the example. Here, with the Kalman filter, it's going to be a different prediction equation. With your robot car, if you're doing X, Y, and bearing, it'll be, three estimates. It'll be estimating X, estimating Y, estimating bearing in our prediction step. Okay? Here, this is our little equation. Now, also, this is where, and again, this is a factor I kind of just play around with, in other words. We also have to be keeping track of our trust, or 1 over trust, our variance. And so our new variance is what our variance was previously, plus this Q value. Okay? And I guess they talk about this being K given K. I've never played with this being a varying Q, changing Q. I've always, when I've done Kalman filter, it's just a constant. All right, some factor, again, of how much we trust the model compared to how much we trust the sensors. Okay? Well, so yeah, and compare. But this right here is saying how much we trust this prediction step. And you got to be careful here when you think about this. Yes, we saw that the robot car, our little robot car, when we tried to find out where it was X, Y on the course, for example, we found pretty lousy. Our wheels aren't perfectly straight, are they? The robot, even when you give them the same control effort on both, same speed, it kind of veers, doesn't it, a little bit? Right? We've got 3D printed wheels, whatever, right? It's not the greatest dead reckoning system. But still, now that's what you kind of think about. This is over 1 millisecond or 4 milliseconds, whatever, however often you're doing the step. So this Q is how much do you trust where you are at 4 milliseconds later? Or maybe just 30 milliseconds, whatever, kind of at the same rate at which you're getting your sensor readings or something like that. So it's very possible that you trust this. It depends. I don't know. I haven't tried it with a robot car. But it's possible that we trust this prediction step a lot more than we do our sensor reading. Because our sensor reading is going to give us, delta, maybe plus or minus a millimeter, plus or minus a centimeter, whatever it is, or your distance sensor, your ultrasonic, those kind of things. Ultrasonic's not going to do a great job of knowing the difference between an inch and 2 centimeters and 1 centimeter and all that kind of stuff. So yes, it gives us it doesn't drift. That's the problem with this guy, right? We're integrating this. Wheels slip. We don't have straight wheels, all this kind of stuff. So we are drifting, but within that little bit of time, we do, over 30 milliseconds, for example, you should probably trust your robot car pretty good where it's at. See what I'm saying there? Anyway, something to think about as you're tuning those values. Okay. So we're keeping track of this. Then we have the correction step. And as we said, just get it all right here, we have that X correct. Yeah, X corrected, which, by the way, in the next sample will be this right here. Does that make sense, right? After we've corrected, this will be the value that we use in our prediction step, the next sample, as our most current thing. Okay, so corrected, and I'm going to get the notation. Oh my goodness. Am I hitting the buttons or something? Doing something with my pen. Okay, go back to here. X corrected is equal to this prediction right here. So I'll use the notation here for a second. This guy plus our K divided by X sensor, which, yeah, let me just fill this just out. Sensor minus X prediction. This is that K plus 1K, right there. Where, again, K is equal to the variance of the prediction, which, well, let's see. Shucks. Sorry, guys. I'm having a real hard time here today. X variance of the prediction over variance of the sensor plus variance of the prediction. Okay, so that's our corrected, and then our variance, let's see, corrected is equal to 1 minus K times the variance predicted. Okay, now how do we write that in Kalman terms? So this is the way we've been talking about it. What we do there is now we divide this up. We make a term called S. S, this value, is equal to variance K plus 1 given K information. That's this guy right up here, okay, which we've been calling the variance of the prediction. Okay, variance K plus 1 plus R. Okay, this is our trust, 1 over the trust in our ultrasonic sensor or whatever sensor we're using. Okay, so we set that, and then we say that K is equal to the variance K plus 1 given K over S. Okay, and so that's this right here. Do you see that? That's our K, variance of prediction divided by variance of prediction plus R, or trust in the sensor, 1 over the trust in the sensor. Now, why are we doing this S right here? Because in a multi-sensor, multi-degree of freedom or whatever state, a matrix setup, we are going to have to find the inverse of S to calculate that. So that's why we specify this term as S. Right now, it's no big deal, right? We can just divide. But when we get to multiple states, this S term will be a 3 by 3, 6 by 6, whatever, right? And we will have to find the inverse of this sucker. Okay, good. To find K. Good. And so then we've got our calculation for S and K. And so our final form of these two equations now for the correction step, and this is a way I've seen in a number of papers. I'm sure they do notation differently in different papers. But now this is saying, all right, and it's kind of weird. It's saying X, K plus 1 given the K plus 1 prediction is kind of what that's saying. All right. So this notation really confused me the first time I was reading through the papers. But it's that K plus 1 given K plus 1 information, which doesn't sound right because, well, anyway, but that's what they're trying to say there, kind of, is equal to that prediction, that the most current prediction that we have right here, this guy, what? Plus K times, okay, now, in Kalman terms, Z is our measurement. And so Z here is our X for example, sensor or, you know, ultrasonic or whatever, right? So we have then that K is Z, our measurement, minus our most current prediction. Oops, K. Erase. Oops. Draw. Okay. What? Draw. There we go. Okay. So there is our correction step for the our estimate. See that? Okay. And then, of course, we'll notice here, variance, when you sum something new, as long as, you know, variance is positive, that Q is positive, if we just do prediction, right, this variance is getting larger and larger and larger and larger. So that means we're trusting the prediction less and less and less and less and less, aren't we? And if we never do a correction, this variance is just going to get huge or whatever. It's just keep on building up and up and up and up. So we need to we have to update our variance with this trust we have in this sensor reading that we got. Okay, and so that's very important. Otherwise, you know, it's not showing the right stuff. So we've got to down here not only find our prediction, but we also have to correct our variance. And so the variance, K plus 1, K plus 1, kind of saying this is the variance we're going to use in the next millisecond or the next sample rate, equals 1 minus K times what our predicted variance, what our variance of the prediction was at that moment. Okay, so those are their steps. So the full Kalman filter then is we do our prediction. Then whenever we get the new sensor reading, it does not have to be every prediction step. Whenever we get a new sensor reading, we calculate S, we calculate K, and then we correct with that K, and we also update, correct our variance, our trust now, one of our trusts with our K also. Okay. All right. And so what you'll see, did I pull up the PowerPoint? I did not pull up the PowerPoint. What you'll see in papers probably is PowerPoint lecture. Sorry, should have had this up. Here. Okay. Let's go down. And well, this is what you'll probably see as the general form. In our case, F is the identity, right? We just have, if you recall, for our little thing, it was just xk plus v times delta t, wasn't it? Right? To integrate minus v times delta t. So anyway, with that little equation. So, but you'll see it generally in that form. And then, right, so here's our prediction. Here's our new updated covariance. All right? These are all matrices now. This is the vector of states. This is a, you know, 3 states. This would be a 3 by 3 matrix. This would be a 3 by 3 matrix. Depending on how many inputs there are is the dimension of B, right? Okay. So we have that prediction step. And then the correction step, Y, right? So H is our C. Maybe you're more familiar with that in state space form. But it's saying all of the states that we can measure. What are those states, right? We want to know the estimate that we have right now of those measurements. We're from those are being subtracted from Z, which is the measurement of those states. So, for example, in the for the robot car, when we got X, Y, and bearing, in my mechatronics class, we use the camera system. And it sends the XY bearing of what the motion tracking says the robot's at. And that would be the Z measurements from the motion tracking. Right? Now, what I like about that motion tracking in there, and I don't change it, there's a kind of a corner in that 12 foot by 12 foot where the motion capture doesn't work as well. And so there's some times when the robot is not seen by that camera system. And during that time, it's got to rely on its dead reckoning. But when it finally gets in an area where it sees the robot again, boom, we apply this correction. And it doesn't correct it immediately, but you'll see as it gets 1, 2, 3, 4, a couple different, it kind of converges back to where it's supposed to be. You can see the car going back to its right position. Anyway, so we find that error, measurement to what we are currently estimating, find our S, okay? Then, of course, see, that's the kicker here. You got, if you keep on adding more and more states to your Kalman filter, it becomes more and more expensive. You got to be careful there, right? Computationally more expensive. And then here's our K. Then we correct our state with this magical K times Y. Okay, we just trust that it works right now, right? Trust in the mathematicians and the control folks. Trust in Professor Kalman, right? Anyway, and then remember we said 1 minus K times our previous variance, right? But this is the identity minus K matrix times H. And then that's our updated prediction, our updated covariance matrix. All right. Good. All right. Now, there's, as you read through papers, they finagle with, what, to make some things work, what should be your U, what should be your states and all that. That's always kind of the, genius behind some of these Kalman filters that make things work, is playing around with what model do we actually use and what do we use as our inputs. For example, in the, you would think in the quad rotor, right, our only inputs for the Kalman filter would be the torques that we're adjusting the motors to be, right, to fly the quad rotor. But in the Kalman filter equations for estimating the states, at least from what this company BitCraze that makes the crazy fly, right? And I think it's common amongst other quad rotor development. Instead of, for estimating where this is XY, given an optical flow measurement too, they have that information. The inputs into the Kalman filter equations are not torques of the motor, which, that's what my brain would think first, but they actually use as their inputs this flow measurement of the optical flow to give them an XY. So, in other words, the input to the system isn't necessarily the torque that then has dynamics that makes the things tilt or whatever. Instead, it's just, maybe making some assumptions that dynamics is really fast and we don't have to worry about it. So instead, we're going to give as input that flow measurement and then also the gyro readings, which I think of those gyro readings as feedback, right? And I would think that would be a measurement right there, a Z. But instead, in their formulation of the Kalman equations, they put it here as U. So all I'm saying, it's just, there's many ways to work these equations, is what I'm just trying to say. I'm sure as you get into that more, you'll see more of that. Yeah. Yes, I believe so. Anyway, I just wanted to kind of say that. So people move these all, change this up just to make it work. They try things out, and then if it works, they use it, right? Kind of thing too. Okay, well now, how do we use this for the Segbot? All right, let's just look at that really quick. And for the Segbot, what do we have? What we need to know is we don't have directly a good measurement of tilt of the Segbot. We have a great measurement of velocity. The velocity of the wheels is excellent. That's a great feedback signal. A little noisy maybe, but a good feedback signal. The rate of tilt of the Segbot is also a good responsive measurement because that gyro gives us directly the rate of change, rate of tilt of the Segbot, the gyro axis does. So that's a good measurement. So we got that one, we got the wheel velocity. Yes, we do have a tilt measurement, but if you kind of remember from lab 5, was it? Do you remember that we set it up so that we are filtering the accelerometers with a 5 hertz bandwidth? You kind of remember us looking at that? Anyway, what we're doing is we're filtering the heck out of the tilt measurement. Now, again, it's acceleration, but we're not interested in how fast we're accelerating this way. We're, you know, and an accelerometer, a little MEMS accelerometer, is kind of like a cantilever beam anyway, right? And so if we tilt, there's going to be gravity pushing on the cantilever beam, right? And that's what we want to sense. We're not really interested in the, you know, how fast we're accelerating. So that's why we filter it so much. And it does give us a good tilt measurement, but it is super delayed, okay? And that delay doesn't allow us to balance the Segbot very well. So we do have a way to get tilt also from the gyro, don't we? We can integrate the gyro, and we do. So we integrate the gyro, and that gives us tilt, doesn't it? The problem is you sense that gyro reading, and it's got noise on it. It could have a bias. That bias could change a little bit, right? You know, when it's sitting still, it may be not exactly 0 and all this kind of stuff. And that temperature can cause that bias to change. So we're sampling that, and what happens to an integral, if you have a little bit of error, the value that you get for your angle starts drifting away, doesn't it? So that drift is our problem of the integration of the gyro. So to correct for that, we want to trust the accelerometer reading a little bit, right? And what is it telling us? It's giving us, you know, over, let's say, you know, it takes about 50 milliseconds for it to get to the right angle. It's that much delayed, let's say. I don't know what it is. We have to measure it. But what we're doing is we're saying, okay, I do trust this some, so that you need to know that this guy doesn't drift very much at all, actually, the acceleration value. So, you know, it's how the gravity is working on this little cantilever beam. That we do know that it doesn't drift, but for the responsiveness, the integral of the gyro is much better to use for your control. Okay? So what do we do there? All right, let's even just look at the code. And this is what you guys implemented in your code. So let's see if I can put them both up here. Both the equations and our code here. So yeah, okay, look at this. So what are we doing? Kalman tilt is just our most current prediction, okay? And tilt rate is, look at tilt rate here. See, it's gyro x in terms of radians per second. Kind of remember that? Okay, so we were kind of printing that out. Tilt rate, okay? We now say that this is a very simple, we don't, you know, again, we're using backwards rule to integrate tilt rate. Tilt rate is equal to our previous tilt, okay? So our previous tilt plus a little sliver of the integral, we call that prediction tilt, okay? Then also, how much I 1 over then my covariance, again, just a scalar. This isn't a matrix, is it? That's what's really nice about this, is just one sensor reading, one state, the tilt, is my Q plus my Kalman P. So just, and again, my previous covariance, what that is. And then this is my new predicted covariance. Now it's interesting, with this accelerometer, we can read the accelerometer every 1 millisecond. Okay? So we're actually doing the prediction step and the correction step every millisecond. Kalman Filter doesn't require that, but we can in this case, just because we're getting those readings at the same rate. Okay, so I've got my prediction step. Now here's my correction or update state. My measurement of this tilt, I'm assuming to be directly the accelerometer. Now, of course, better, what would you find if you would convert the radians, calibrate the radians of that tilt measurement to actual G's of the accelerometer? You find that the correction between those two, or the conversion between those two, is very close to a factor of 1. That's why I'm just using, because technically we should convert G's to radians here, shouldn't we? But I'm being lazy because we'd have to calibrate that. We'd have to do some kind of measurement. But what you find is that's pretty darn close to 1. Anyway, just happens to be. Maybe in other systems that wouldn't be the case. Okay, so we find our measurement Z of that tilt. We find our Y error, right? So we're right here now. Y error. We then find our S, which was our covariance from the prediction step, plus how much, 1 over how much we trust the tilt sensor, the accelerometer as a tilt value. Find our K gain, right? Right here, right? K is covariance divided by S. So do that. And, I put it all, you could of course make this all nice and maybe 1 line of code if you wanted to, probably. But I wanted to shell it out all into the way, so it looks like a Kalman filter in the equations. Then my corrected tilt is equal to what I predicted, that sample, plus the Kalman gain times that error, okay, the error Y. And then my corrected covariance is 1 minus the Kalman gain times that the predictions covariance. See that? Okay. And then you're ready to use what? You're ready to use Kalman tilt. And that's what we do. Kalman tilt is our best guess or best information we have to that point. That's what we will use in our controller for the tilt. Okay? And now your goal, as I said, great, I can write down these equations, but you need to know what is Q and what is R. Those are the two unknowns. That's when you get this Kalman filter, how do you come up with those values? In a matrix system, a lot of times you can start out with a Q and R that's just diagonal. And that works kind of nice. You don't have to think about all the off terms. You'll see if that works. Now, of course, in this case, it's just a scalar. So I just need to know what's the relative difference between, or what's the difference between Q and R here. And you'll find that I think I use Q as 0.01 and R is 25,000. Works well. Now, there's other numbers that work. But in other words, we're saying we trust the integral of the gyro way more than we trust the accelerometer. Let's see if I can get to Q quick. There it is. Yeah. So Q is 0.01 and R is 25. If you put R at like 20,000, it's still going to work too. So there's quite a number of different Q's and R's that would work to make this. But what one group, and I'm going to let you go, one group accidentally put R as the radius of their wheel. They changed their code because they saw I was using R. They were also using R as the radius of their wheel. And they changed some things up. And it ended up being that, they had made R 0.19 something. Well, that wasn't a big enough gap between Q and R, and their robot just shook like crazy with this. It took me forever to figure that one out. But anyway, so obviously there is it does have to have some range difference between each other, orders of magnitude. But anyway, it worked for this system. Great, very good. Okay, so I will see you guys in lab the rest of these weeks. Thanks a lot.
On this.
Yep.
That's down here.
Oh yeah, go back to it. Sure.
Yeah, if you don't mind. Just wanted to make sure I wasn't going crazy here.
Sure. Let's see if I messed up. Go ahead.
Right here. So if these guys weren't running at the same rate, so let's say I was predicting more than I was estimating.
Yep.
Or more than I was correcting. Where was it? Right here, that would actually be the previous predicted tilt value.
Right.
Okay.
Right.
Okay, cool.
So how would we do that? That's a good point. That's a good point because
Like I said, it only matters when they're running.
Kalman tilt's getting calculated there. That's right.
Okay.
So you would say, yeah. I guess you would have to down here. How do I do that in? Did I give you that code?
Yeah.
How did I do that in that one? Because that's definitely happening at a different rate. I think what I did is, yeah, what I probably did there is I would say right here, Kalman tilt equals predict tilt for the next time, right? So in the normal prediction, right, this would be like the old state. Boom, boom. And then down here, in the same way, after I'm done with the prediction step, I just set Kalman tilt right here. Do you see what I'm saying? So really, could be called tilt k minus 1. And right here, we're saying prediction tilt, tilt k minus 1 is equal to tilt k. So the next time in here, we use it here, right? And you're right. But then what we would do down here, right here, we would also say this is equal to tilt. Let's see.
Yeah, couldn't you just modify the pred tilt the entire time?
Yes, I could.
Okay.
And maybe that's the way I do it.
Okay.
Yeah, maybe that's how I do it.
Okay.
In your code that I gave you.
Yeah.
But anyway, yeah.
Cool.
You're totally right. You're totally right. Yeah.